Process datasheet PDS, which is one of the most critical deliverable in process industry. This document is the starting document for various disciplines to start their design. So it has its own importance. In this section, we are going to discuss what is process datasheet, what are the various sections, what are the various parameters which need to be there. To understand in a better way, we are going to discuss two different examples. One is tank datasheet, then we'll look into the pump datasheet also. Along with that, we are going to understand what are the various parameters. For example, the pressure, atmospheric pressure, the specific gravity, right? NPSH, cavitation, suction pressure. So all these factors we'll look into so that we can understand how we put these parameters into the process datasheet and how it is being used for various activities. So let us start with this section. We'll start with the basic definition of process datasheet. So what is process datasheet? Let us look into the basic definition. If you look at this section, essential process data for initiating the detailed design. So whatever data is required when we are going to start our initial detail engineering, each and every discipline will be looking at some kind of process data to start their own activities. So this is the initial document which will be facilitating all these disciplines to start their design work. Right, this document will be including a lot of things. For example, the overall size, approximate geometry, identification of various connections. So if you look at any of the process datasheet, there will be some tentative dimensions, right? All the connections, nozzle connections will be there along with tentative sizes. So those kind of information will be there. Then along with this information, there will always be information related to material of construction and full range of operating conditions, right? So this kind of data will be very much useful for any other discipline to start their own design activities. One more thing which is really very important here, these sheets will incorporate the information which we are going to select, right? Along with that, there will be few inputs which will be required from vendor side, right, which will be visible in the process datasheet after the purchase is done. So those columns, those rows will be empty during initial stage, and once these information is further developed with the help of other discipline also, along with various interaction with the vendors, those empty spaces will be filled. So this, once it is discussed with all the vendors, then only it will be a complete PDS. Otherwise, the basic operating conditions and tentative dimensions along with some connection details will always be there. So this is something which is process datasheet is and is very much essential for all the discipline to start their detailed engineering. So in this section, we are going to take an example of tank datasheet so that we can understand what are the various sections and how the process data is filled. So what we are going to cover here, we'll try to understand the basic things related to all the nozzles which are associated with any of the tanks. Then we'll look into the tank volume and dimensions. We'll try to go through few of the calculations also so that we can understand the basic concepts. Then we'll look into low and high levels in tank, how these are important and how we are going to calculate it. So we'll try to get the basic understanding. Then we'll look into the various sections of actual tank datasheet, right, so that we can understand what we are going to cover in the tank process datasheet. So let us start with this topic. This slide has nothing to do with process datasheet topic, but just to remind you that we have published 8 courses on piping engineering. This is related to piping engineering elements, codes and standards, plot plan development, 7 modules of piping material, layout and design, isometric, tank layout, underground piping. You can go to this link, udemy.com/user/Atul-Singla-5 to enroll to any of these courses. You can contact me at oilandgasconcepts@gmail.com. In any of the tank calculations process datasheet, we have to go through the volume of the tank, which is really very important. first of all we need to understand from where we are going to start our calculations, and from where we are going to get our basic informations which will be required to perform various calculations. So for calculating any dimensions of any of the tanks, we need to understand the volume and consumption rate. This is really very important, and from where we are going to get these two values? We are going to get it from heat and mass balance or utility balance diagram drawings. So these are the various drawings which are developed at very initial stage of the project, from where we will be getting these two values, volume and consumption rate, right? How much we are going to store and how much should be the consumption rate, the flow rates. So in this case, for example, we are taking an example of any of the typical tanks, right? And we are assuming the volume required, which we have received the data from heat and mass balance diagrams, is 12 meter cube, and the consumption rate is 0.5 meter cube. These two values we will be getting from these drawings, and this will be the starting point to calculate further. Now again, at the same time, when we are designing a tank, we don't want we don't want to increase the length. At the same time, we want to optimize the diameter also, right? So when we know the volume, with the help of pi r square h, right, we can calculate the volume, but at the same time we want to optimize the length and diameter also, because if we increase the length, then there may be additional wind loads, or as you know, the depth thickness of the tank varies along with the length, so we don't want to increase the complexity into our design. So these two factors we need to optimize. So there are few thumb rules which we use at the starting of our calculations, that is L by D is equal to 0.5. so we start with this, right? This is in between, so that we can optimize the L and D. So once we start our calculation, we know our volume is 12 meter cube, right? Pi d square by h, we can always put this value as L by D, and we are increasing square to cube, right? This is same. L D we have increased, it is cube, so it remains same. So L by D we are putting 0.5 here, so that now we have only one variable which we need to calculate, that is diameter. So with the help of this formula we can calculate the diameter, and with the help of this ratio we can calculate the length. So this is how we calculate the tentative dimensions of the tank at very initial stage of the project, and this data we fill in our process data sheets also. In any of the tanks, nozzles are really very important. There are few nozzles which have their own purpose, and these nozzles are associated with most of the tanks. For example, if you look at inlet and outlet nozzles, we are storing something in this tank, so there should be some inlet nozzle, right? And we are getting this fluid which we are storing here, we want to transfer somewhere, so there should be an outlet nozzles. So these are the basic things. For example, vent and drains will always be there. There may be a different kind of draining arrangement, but this drain and vent connections will always be there. Then we don't want something to, when suppose any of the signal is not working and the flow is more than its capacity, so we want to have some opening so that it can get out of the tank after certain level. So this overflow nozzle will always be there. Again, at the time of maintenance or after the maintenance activity, there may be a requirement of purging, so purging nozzle will always be there, right? Maybe it is not a permanent connection with the nitrogen line, but this nozzle will always be required, whether it is a local connection or a permanent connection. Then at certain point somebody has to enter into the tank, so there will be few manholes based on the diameter and height, based on the volume. There may be more than one manholes, but this will always be there so that somebody can enter into the tank and perform the maintenance activities. Again, the temperature nozzle will always be there so that we can measure what is the temperature of the fluid which is stored inside the tank, right? Along with the gauge hatch. This is again something at the top. It is nearly like a manhole, but we are not entering into it. We can look into the tank through this nozzle manually. Again, level connections. There may be different kind of levels. If you look at, there are few level connections, some differential pressure connections, and maybe radar type. They have their own purpose. For example, sometimes we only need to measure the level of the tank, so there is different type. There may be a radar type which may be used to trip the pumps which are connected with the tank. So there are different kind of level gauges with its own purpose. So these kind of connections will always be there within the tank. So these kind of connections, these kind of nozzles which are associated with any of the tanks, right? If you look at these blue colors, these are the nozzles which are associated with any of the tanks. This will always be there in any of the process data sheets, right? So this is very important. We need to understand, and we need to tentatively calculate the sizes, ratings, right, based on these services. So this kind of information is required in process data sheets. Now let us try to understand the pressure calculations. If you look at any of the tanks, the first and important section in any of the vessels, it will be vessel design data. If you look at this section, there will be internal design pressure, external design pressure, and operating pressures. These are the pressures which are given in the form of water head, right? So operating and design pressure conditions in the form of water head are given by process in process data sheets. At the same time, pressure including the static head shall also be calculated by mechanical static team. Okay, as in the previous slide we had considered 12 meter cube of volume which we wanted to store in this tank, right? So that 12 meter cube volume will be between LLL and HHLL levels. So this much area, this much space inside the tank will be taken out by should be designed for 12 meter cube, right? Then this portion which which is indicated by LLL level is decided based on the 650 API 650 criteria that says how much spacing should be there between nozzles, right? For example, in this case, if you want to calculate the LLL level, the suction nozzle has to be spaced from the bottom, right? So minimum spacing for 2-inch nozzle is around 175 mm, right? So in this case we cannot place this suction nozzle below that. So considering some safety of factor, we can consider 200 mm elevation from bottom of the tank to this nozzle. So that means this LLL will be around 200 mm. So this kind of volume will be the dead volume. So whatever is the volume required for this, for any of the process plant, for example in this case we have considered the 12 meter cube, that will be stored in this area. In addition to that, this will be there. So LLL low level will be this one. Again similarly there will be some consideration. We need to keep some space above the volume which is required, that is 12 meter cube, which will be filled up to this. Above there can be some surging in the flow at the time of entrance, or some seismic conditions, there will be movement, so we have to keep some space above that. So that will be the criteria to decide the HHLL level, right? So considering all these factors, we decide the dimensions. In previous slide we calculated the diameter and elevation. In those elevations, in the length which we calculated in the previous slide, we will add this much space and this much space, and we'll come up to this elevation. So these are the few of the factors which we need to calculate to define in any of the process data sheets. So let us look at various sections which will be there in any of the tank process data sheet. This section we just discussed vessel design data, where various Pressures are mentioned in the form of water head. Temperatures are there based on the process conditions, right? Liquid specific gravity is mentioned. So this is the basic process data. Then based on the service, for example, if we talk about a DM water tank, then there will be a some material which we need to specify in the data sheet. For example, here we have taken the stainless steel plates. So this data will always be there in process data sheets. Then along with that, there will be some accessories by a vendor, right? There will be some ladders, roof handrail. These kind of things will be filled by vendor. When we discuss, when we communicate with various vendors, they will provide a lot of information and that will be filled at that time. So initially these columns, these rows will remain empty. Then there is a section which talk about the structural design. We talk about roof load, roof welding, etc. Again, this will be filled by vendors. When we start talking about these designs with various vendors, this information will be filled. Along with that, the shape is also covered. What kind of tank we are going to have, that will be mentioned here. Again, cleaning and painting, surface preparation, internal and external surface, etc. are generally filled by the vendor, right? So this is the process data sheet where a lot of process information will be there and a lot of information is empty, which will be filled by vendor or at the later stage of detailed design. Pump data sheet is again a very important document which is related to pumps, and it is prepared at the very initial stage of the project, and this will be the starting point to design any of the pumps. So let us see what kind of information, what are the various critical parameters which are mentioned in these documents. First is capacity, differential head, NPSH, then power requirements and material of construction. These 5 sections are very important in any of the pump data sheets. If you look at the capacity, right, it is generally measured in meter cube per hour, right? Process pump, if it is a process pump, then PFD and heat and mass balance diagram will be required. If it is a utility pump, then this information will be coming from utility balance diagram. So this information is very critical, and these two documents will be the source of this flow rate, this capacity. So there are few things related to capacity which we need to understand: normal capacity, design capacity, and minimum capacity, right? So minimum capacity, we sometimes we call it turn down the capacity, at what capacity this pump will be running. So this information will be there in any of the process data sheet which is prepared for pumps, right? Again, differential pressure, what is the difference between pressures at suction and discharge, so that information will always be there in process data sheets. NPSH, net positive suction head, which is available at nozzle, and what kind of suction head is required at that nozzle. Those calculations are really very important. We will be doing in this section in detail. So that will be part of any of the process data which is designed for pumps. Then power required to run the motor. This information will be discussed between mechanical and electrical, and again this can be a part of this process data sheet. Material of construction will also be there, especially for casing and impellers, and most of the cases, most of the parts material will be decided at later stage once we start discussions with the vendors. To understand various pressure parameters which are associated with any of the pump data sheet, first of all we need to understand what is atmospheric pressure, right? What are the various concepts behind calculation of atmospheric pressure. Then pump inlet, again there will be a pressure at pump suction nozzle which will be having few things which we need to understand related to fundamentals, for example the cavitation, etc. These things we need to understand, then only we can calculate the pressure at the pump inlet. Then specific gravity, Specific gravity is something, a very critical property related to any of the fluids, which will be defining many things related to various fluids which we use in process industry. So this is again a very critical factor which we need to look into. Then net positive suction head, again it is available and required head at pump nozzles. So again there are few parameters and calculations which are important, which we need to perform at various point of time, so that we can decide few of the parameters in process design, process data sheet. So these few things we are going to discuss in detail, so that we can understand pressure related parameters which are clearly defined in any of the process data sheet for pumps. This slide has nothing to do with process data sheet topic, but just to remind you that we have published 8 courses on piping engineering. This is related to piping engineering elements, codes and standards, plot plan development, 7 modules of piping material, layout and design, isometric, tank layout, underground piping. You can go to this link, udemy.com/user/Atul-Singla-5 to enroll to any of these courses. You can contact me at oilandgasconcepts@gmail.com. To understand atmospheric pressure, we need to look into few things. Okay, if you want to calculate the pressure because of atmosphere, we will have to look into this configuration. Okay, it is cube with 1 inch length, that is area will be 1 inch square, right? And if you take the length of this cube, which is equivalent to the atmospheric thickness, then whatever pressure will be there at the bottom of this section will be our atmospheric pressure, right? So this is atmosphere thickness and this is 1 square inch. So whatever pressure will be indicated, that is atmospheric pressure. So in this case it is 14.7 pounds. Okay, so if you want to convert this atmospheric pressure into water head, then we can do this with the help of this figure. If you make a 1 feet by 1 feet cube along with 1 feet height, and we fill it with water, right? So its weight will be 62.425. that means this much weight of the water which is filled in 1 by 1 by 1 cube will be this. And if you convert it into inches, that is 12 inches per feet, then 12 by 12 by 12 is equal to 1728 cubic inches. Now if you divide this much weight of water by this many cubic inches, you will get the pound, this much weight will be there inside this volume, right? Now we know this much pounds of atmospheric pressure is there, and this much pound weight of water is there in 1 inch cube meter, and if you divide these two factors, you can easily get the value in feet, right? So this many inches, sorry, not feet, this many inches will be equivalent to this much atmospheric pressure. And if you convert these inches into feet, you will get the 33.9 feet of water head is equivalent to 14.7 pound. That means we can easily convert the atmospheric pressure into water head. So this is the atmospheric pressure and 407 is the water head, which is equivalent to this much pressure. Now we know 33.9 feet of water is equivalent to 17.4 psi, 14.7 psi. That means 1 psi will be equivalent to 2.31 feet of water head. So this is something which is Very simple, but we need to remember how these values are coming. Now these we calculated in the form of PSI units, but we can always convert it into bar. So 14.7, this atmospheric pressure is equivalent to 1 bar, right? So we can calculate into SI units also. So similarly, same configuration, if you use 1 psi is equivalent to 2.31 feet, you can convert any of the psis into water head. So we know 1 psi is equivalent to this, then 20 psi will be equivalent to 46.2 feet. At the same time, if you want to reverse calculations, then 100 feet is equivalent to 43.29 psi. So this conversion we can utilize in various calculations at various point of time. Specific gravity is again a very critical thing to calculate various factors in process industry. What is specific gravity? The weight of any liquid relative to that of water is called specific gravity. In previous slide we checked that 33.9 feet of water is equivalent to atmospheric pressure, right? If you use this specific gravity, we can calculate the head and pressure with respect to any other liquid. If we divide it with specific gravities, or we can multiply in this formula, we will be getting these two factors. Now there are two kind of fluids. One are lighter fluids, another are heavier fluids, right? When these any fluid is lighter than water, then these are lighter fluids. That means the specific gravity will be less than 1. For heavier fluid, the specific gravity will be higher than 1. So if you divide this 33.9 feet of water head by specific gravity of that lighter fluid, then we will be getting the head because of that particular fluid with respect to water. Similarly, if you divide heavier fluid, for example any industrial waste you take in as an example, the value of specific gravity will always be more than 1, and if you divide it with the water head, you will be getting the head equivalent to atmospheric pressure with respect to that particular fluid. So this is how we use specific gravity in process industry to calculate various heads for particular liquid. So to understand the net positive suction head, there are few things which we need to understand first. For example, the NPSH available and NPSH required. So absolute pressure at the suction port of the pump, that is available, but at the same time we need to calculate what is NPSH required, so that we can calculate whether we can avoid the cavitation or there are chances of cavitation in the pump. So whatever is the pressure at the inlet, right, that will be governing whether there is cavitation or not. So first agenda will always be to create a pressure differential between inlet and outlet nozzles. So if pressure at inlet nozzle is higher, then it will uh, force the fluid to move towards outlet nozzle which is at lower pressure. So this is something related to pressure differential between inlet and outlet nozzle. If the pressure at inlet falls below vapor pressure, then there will be formation of bubbles in the fluid at inlet. These bubbles will be collapsing rapidly once they start moving towards outlet, right? Once these start collapsing, there may be a noise and there may be which is causing the cavitation, right? So cavitation is a phenomena of bursting the bubbles created because of lower pressure as compared to vapor pressure. So cavitation removes small spots of material from inside the valves, right? So this is something which we don't want. This cavitation is removing some material from the valves inside the pump, that means pitting the valves and causing the permanent damage to the pump. So these things we want to avoid That is why we want to avoid the cavitation, right? So that means the pressure at inlet should always be more than vapor pressure, until otherwise there will be cavitation and it will damage the pump. Now there are few thumb rules which will be helpful to avoid the cavitation, which we can use at very initial stage of the project, so that there is a factor of safety and we can finalize few of the parameters, and at the same time these parameters will help us to avoid the cavitation also. For example, the NPSH available, right, is more than NPSH required. How much difference? 5 feet or 10% of the available, right? So this is a thumb rule. This we can use at very starting stage of the project. For example, if NPSH are, that means required NPSH is 10 feet, then we can always go ahead with NPSH available considering it is 15 feet, right? We have added 5 feet as additional head. Then cavitation occurs more rapidly at higher temperatures. If the temperature is more, then this cavitation phenomena may be more predominant. Reason is pressure, vapor pressure will be increasing with temperatures. So if it increases more than the pressure at the inlet, then cavitation will start occurring. Now there are few things. For example, the pressure gauge measure the pressure relative to the atmospheric pressure. In previous slide we discussed about the atmospheric pressure, but the pressure gauge reading will be relative to the atmospheric pressure. So readout of any pressure gauge is called the gauge pressure. So whatever value is there, we call it gauge pressure, and once we add this gauge pressure with atmospheric pressure, we will be getting the absolute pressure. So absolute pressure is always used, very commonly used term with respect to pressure. So this is nothing but gauge pressure, which is a reading of the pressure gauge including the atmospheric pressure. So vapor pressure of fluid is expressed as absolute pressure. Okay, so we know now what is absolute pressure. Vapor pressure is expressed in the form of absolute pressure. Then this absolute pressure will be used for calculating the NPSH available, right? So NPSH available will always be absolute pressure of the fluid at inlet minus the absolute vapor pressure of the fluid at operating temperature. So this is the basic formula to calculate the NPSH available. So these are the few of the terms which are relevant with respect to pressure, which will be used in so many calculations which we are going to perform in next slide. So now we know there are two kind of net positive suction heads available and a required one. So required NPSH shall be calculated by pump vendor with the help of various performance curves with respect to any particular pump performing with respect to various parameters. So we first need to understand there will be energy requirement to run any of the pump without cavitation, right? That fluid which is moving inside will be losing this energy at various points, right? This energy loss will be there, and some energy is required to avoid cavitation also. So to maintain this, right, there will be few calculations which will be done by pump vendor so that NPSH required is calculated, right? To calculate this, there will be some design factors. For example, how steep the impeller vanes are there, the speed of operation, the shape of volute. These are something which will be taken care by the vendor only, right? And it is listed on the pump curve at your specific design point. So these parameters will be helping in finalizing the NPSH required, right? So we know like 34 meter of water head at sea level will be equivalent to 14.7 pounds per square inch of atmospheric pressure. At the same time, when the fluid will be moving vertically, right? If the water is at lower elevation than the pump, then it will be sucking from bottom. Otherwise, that means there will be a negative head. If the source of water is at higher elevation, then there will be positive head. So there will be losses in both the cases at the time of suction. When it is entering into the pipe and it is entering into the pump, there will be losses. So that means energy loss will again be there. Then there will be friction loss in feeds in the suction pipe, or the pressure lost when the water rubs against the wall of the pipe, and losses created from the vapor pressure, which is a result of temperature of the fluid, right? First one is the suction pipe where losses are there. Again, when the pipe fluid is moving inside that, there will be a pressure drop because of rubbing and because of vapor pressure. So there will be some energy loss in both the scenarios. That means to compensate this loss, we have to add some factor of safety, right? Which will be giving us the value of available versus required NPSH. So in case of storms causing lower atmospheric pressure, again there will be some losses. So all these are uncertainties which will always be there. So we have to take care of these things also along with few of the losses. That means the available head should always be more than the required one, which will be given by a vendor for the smooth operation of the pump. So change in diameters due to corrosion and all, this will again cause some pressure drop. The factor allows the pump to operate in less than ideal conditions. Okay, so this factor of safety will always help to have NPSH available more than required one. So once you know the losses of NPSHA, you can add that to the required one. Okay, then compare it with the atmospheric pressure of the elevation. So this is something which we need to keep in mind while calculating the NPSH parameters, which we are going to calculate in detail in the coming slides. Now let us take an example to calculate the net positive suction head. So this way we will be looking into various factors which are important to calculate this, which we discussed in previous slides. Here we are taking an example of a pump which is sucking water from a source which is at lower elevation than pump, right? There is a difference of 10 feet between center line of the pump and the surface of the fluid. So we are considering it is open to atmosphere. That means the atmospheric pressure will be there on this liquid. Again, this 68 degree Fahrenheit temperature is there, and the vapor pressure for water at this temperature is this much, right? So what we have a static head which is negative, which we call suction lift. If it is at higher elevation, then this should have been positive. Suction valve, we are considering there is a valve, but it is fully open. Water system is at elevation. If it is at sea elevation, sea level, then the atmospheric pressure is this much, which we calculated in previous slides. Friction losses for this particular case is given as 3.2 feet. Right, so in this case what we are going to do, we are going to calculate the net positive suction head available at the nozzle, at the inlet of the pump. Okay, so we have to consider few of the factors here. For example, HA, that is the head from the absolute pressure acting at the surface of the water, which is atmospheric pressure, right? So atmospheric pressure is what? It is 34 feet, which is equivalent to 14.7 psi. Now second factor is head from vapor pressure, right, which is 0.783 with respect to this much psi. We have converted this psi into atmospheric head, water head. Third one is the static head or elevation difference, which is 10 feet in this case. Now we are lifting from bottom, so that means this value will be negative, so it is minus 10 here. Fourth one is the friction head, right? When the water is flowing inside, there will be some friction losses, so that it is given 3.2 feet. So once we subtract these three factors, that is vapor pressure, static head and friction losses, from the atmospheric head, this will be coming around 20 feet. So that means this much pressure is available at inlet of this pump, right? So the system is open to atmosphere, so the absolute pressure above liquid in this example is simply the atmospheric pressure. That is why we have taken the 34 as HA. Now static head we have taken as a -1. So this is how we can calculate the net positive suction head available at inlet of any pump. Let us look at various deductions from standard atmospheric pressure to calculate the net positive suction head. So there are 5 factors. First one is the altitude or the elevation at job site, right? For example, the pump is located 2000 feet elevation, right? There will be elevation correction with respect to sea level. There is a standard table which we will be looking into in the next slide. So that table is standard and used globally, so that we can calculate the elevation losses because of elevation. Second factor is the vapor pressure of any liquid, right? So any liquid will be having its own vapor pressure, right? That should not be more than suction pressure, otherwise there will be formation of bubbles and there will be cavitation, which we don't want in any of the pumps. Third one is the total dynamic suction lift, which is the combination of static lift and friction losses of suction pipe. This will be governing factor to calculate the total dynamic suction lift. This value is also the suction gauge reading during operation at designed flow rate. Again, this will be taken care in next slide. We will be looking in what it is and how we get this value. Again, the safety factor is very important. We need to take some margin so that in any case if there is change in parameters, the calculations remain same. Then the net suction head required, right, which will be based on various factors which will be used during the design of pump, and it will be coming from vendors, different pump vendors. So, but we need to remember that the available head should be more than the required ones for the smooth operation of the pump. So these are the 5 factors. We are taking one example so that we can look into each and every factor which will be used to calculate the NPSH. Now let us take an example where we will be considering all the parameters so that we can calculate the NPSH, or we can verify whether the NPSHA, that is available suction head, is more than NPSHR, so that the pump can run smoothly. So we are taking an example here. Minimum required information to perform these calculations will be flow rate. In this case we are taking 1800 gallon per meter. Then fluid type, in this case we are taking water. Temperature is 100 Fahrenheit. Elevation of pump will be around 2000 feet, and total dynamic suction will be 15 feet. This is a gauge reading. So these parameters will be required to start the calculations. Now the first thing is, because of this elevation above sea level, where there will be some reduction in elevation, there will be reduction to maximum dynamic suction. This factor we have to consider, these losses we have to consider because of this much elevation from sea level, right? If you consider this table which is given, this elevation, this loss will be 2.3 feet, right? Second one is the total dynamic suction lift, which is a combination of static lift plus friction losses, which we discussed in last night. This value is also the suction gauge reading during the operation, right? It is given in this example, that is 15 feet. And vapor pressure at this elevation is 2.9. So if you look at the heads, standard atmospheric head will be 33.9, right? And these three losses are there, which we calculated. 2.3 from here, 15 feet is here, and atmospheric pressure for water, that is here. So these three factors will be subtracted from this atmospheric pressure, and the factor of safety of 2 feet, that will again be subtracted from this head, water head. So we will be coming out with 21.49, right? Again, if you look at the performance curves, mostly this required NPSH will be given by the pump vendor, but if you look at the performance curve, these parameters with respect to the flow meter, that is 18, this is a factor into 100, so 18 will be coming here. This will be giving us, with respect to this pump, like the head required will be around 8 feet, right? So this is just an example of performance curve, and this can be utilized by pump vendors. They will be referring so many performance curves to get up to this value. In this case, we have just taken an example and we have come up to the required head with respect to this flow rate, that is 8 feet. Now it is clear, available one is 12.41, required one is 8. That means there is a head available, extra head of 4 feet is available, more than 4 feet is available, so that the pump will be running very smoothly. There will be no cavitation. So this is how we can use these parameters, and we can compare the NPSH available and required one, and we can calculate many things. In any of the pump process data sheets, there will be few sections, for example, process parameters, site and utility parameters, performance parameters, material. Not only this, but related to construction, base plate, bearing, lubrication, and along with various notes. So process parameter is one of the section which is mandatory. All the mandatory data will be filled in this part. For example, the fluid type, what kind of fluid this pump is going to handle, what is the vapor pressure, relative density, specific heat, viscosity, right? Net positive suction head available, pumping temperature, flow rate. So these data is the mandatory thing which has to be there, and this is coming from heat and mass balance diagrams, right? We have to calculate few things, for example, net positive suction head and differential pressure. Differential pressure is the pressure difference between inlet and outlet, which will be required to design any of the pumps. Along with this, there will be some data related to site and utilities, right? Where we are going to locate this pump, whether it is at grade or some elevation, right? So this kind of things, ambient temperature, relative humidity, this data has to be there, along with some cooling water requirements or something which will be decided by the vendor. Again, performance parameters which will be decided by vendor only at the time of design, but this section is there so that vendor has to, this section goes to vendor and he has to fill that. Along with material section, where we will be listing out what kind of material will be there, right? This is something which is decided by the process engineers and it goes to vendor for further design. Along with that, there will be few sections, such sections related to construction base plate, which are filled by pump vendor only. So this is something related to process data sheet, so that we can visualize what kind of data and what kind of formats are there and how we proceed with preparing such data sheets. So in this section we talked about process data sheets, which is having all the data to initiate any of the detailed design activities. Along with that, we looked into various parameters, pressure parameters, like what is atmospheric pressure, how we calculate the water head, NPSH requirement, inlet pressure at pump nozzle, various type of nozzles in tanks. So all those things, all the various sections available in datasheet we looked into. So this will be covering the basic understanding, basics behind developing a process datasheet. So thank you for watching. Keep watching. Stay tuned.